Okay, welcome back. Hope you had a nice lunch. Welcome to the last session, which might start now and end, we don't know when.
At Scribe Plus. Okay, so, okay, good. Come along. You're almost there, but there's no time to waste. Okay, so where are we? We went from the global back to the quasi-local, and what I want to discuss now is some characterizations of what this row, this mixed state, which in its simplest form we're going to view as the mixed state that comes from formally tracing out the right part of the Hilbert space. So imagine that we partition. This is formal because of the issues of partitioning quantum field theory Hilbert space locally. But as a sort of guiding cartoon, imagine that we partition the space of all states on a global slice into a tensor product of left and right states, and tracing out all components of the right Hilbert space, formally, to remain with a mixed state operating in this region over here. And as our state on the complete slice, we'll take this Hartle-Hawking or Bunch-Davies pure state. Okay? And I want to discuss first the QFT problem, and then I'd like to discuss what ideas people have about extending it to gravity. Let me make some general characteristics about this state. So we have now a region, a portion, a finite-sized portion of space-time, of the universe, which is, like I said in the first lecture, is governed by this metric of the static patch. And it's a very simple static metric. We have these time translations, yeah? So it's a sort of, there's a natural notion in QFT, if we don't have gravity, there's some sort of quantum field theory Hamiltonian that evolves us along these slices. Yes, you can imagine some static patch Hamiltonian that evolves us along these slices. That is the generator of the isometry associated to translations in T. And that's the SO1,1 subgroup of the SO4,1 in terms of our isometry group, okay? And we also have this S2 over here, which is the SO3 subgroup of SO41, which is the, well, it's the sphere that surrounds the observer. The observer sitting at psi is equal to 0. Yeah, that's our inertial whirl line. And we're surrounded by these celestial spheres, if you will, which are these d omega squares over here that as psi increases, they go up. Sorry. Okay, that's what was confusing me. Excuse me. Terrible. Okay, better. Yeah, so at t equals 0, the space-time, at psi equals 0, the space-time looks effectively like a little portion of Minkowski space, yeah, surrounding us, a little like this room or the solar system. And then as psi increases outwards, you start to see toward pi over 2 the redshift effect on time. And that's sort of in our world, this would be when you start approaching celestial spheres of the size of 10 billion, 20 billion light years. And finally, we end with this cosmological horizon over here. That's the natural end of our observable world. And so we would like to see if we can effectively describe some of the physics in this finite portion of space-time. Now, so that's the setup at hand. And let me already make one more comment about this, which is that we can already anticipate some of the properties of this row over here, because I had written down in a de Sitter invariant state, we know that the correlation functions around any 2 points, so let's discuss the 2-point function for a moment, are themselves de Sitter invariant. I'm assuming here that there is a state that preserves the de Sitter symmetries. And what that means in particular is that in the embedding space picture, they were functions of this x a y b, where x and y are coordinates on R1, 5 projected onto this hypersurface, yeah? But they have a very particular property, the correlation functions in de Sitter, which was mentioned also in Derek's lectures, a similar feature, which is that if I study them in the Euclidean continuation of time, yeah, so I could study the analytic properties of the Green's function, and I could in particular study them in the Euclidean section of the geometry. And what happens to the static patch if we take t to minus I tau? So what happens is that you get the following metric, which is d tau squared cos squared psi plus d psi squared plus sine squared psi d omega squared. And this metric may or may not look familiar to you. Well, firstly, we would like this metric to be smooth, yeah, because we'll be interested in gravity as well. And that means that when psi approaches pi over 2, tau cannot be valued on the whole real line. Yeah, I hope that's clear, because when we approach psi as pi over 2, this is going to cap, yeah, and so we're going to have a piece of our space that would cap in a singular way unless tau is in fact periodically identified. Okay, so the natural smooth continuation of the space requires that the Euclidean time is periodically identified, and therefore correlation functions naturally, right? So when you continue to Euclidean signature, this SO1, 1 continues to an SO2 subgroup of the SO5 isometries of the phi sphere. And so if your correlations are invariant under this SO2 compact group, yeah, another way to see that tau has to be periodically identified is that it generates a compact subgroup of SO5, which is SO2, yeah, is that our Green's functions obey what's known as the KMS condition, namely that they have periodicity properties in Euclidean time. And that's the characteristic feature of a thermal state, yeah, so periodic in time correlations in Euclidean time. And so, at the level of QFT, it appears that this rho is a rather special mixed state. It's a thermal state, yeah? So at least if it exists at all, which when we split QFT in these portions is not really a correct statement, but the properties that it would have are those of a thermal density matrix. Yeah, so, and thermal, of course, if I tell you thermal, I have to specify with respect to what Hamiltonian and at what temperature. So it's with respect to the static patch Hamiltonian. And with which temperature? Well, with this temperature, which is the inverse periodicity of the Euclidean time, which is the de Sitter temperature. And indeed, one can calculate this temperature in a variety of ways. You can use the method of Unruh, who calculated it for very general horizons. And indeed, the manifestation of the Hartle-Hawking or Bunch-Davies state in this portion of spacetime, as measured with the clock of the static patch, is that of a thermal state, a characteristic feature of horizons at large. Yeah, so there's a certain thermality associated to this state. And what we'd like then to do, so that's already quite useful. It's a rather stringent characterization of this density matrix in the space of all density matrices. And so we'd like to understand, in a sense, at least formally, if we can make any sense whatsoever of the following object, yeah, which I'm going to stop using quotation marks in a moment, but so there's a thermal density matrix that we're interested in. So given let me rephrase. Given the following density matrix over here, static patch, yeah, where beta is 2 pi L. And here we can normalize as well if we assume that the trace makes sense for this thing. But formally speaking, we'd like to understand properties of this, and the simplest kind of property we could imagine studying is something like how much thermal entropy it codes. Yeah, so this could be a simple example. It's not by any means the only example, nor should we be obsessed necessarily with entropies as opposed to other interesting quantities in thermal systems. But this is a quantity, a characteristic type of quantity that we may be interested in understanding. Yeah, sort of the thermal entropy. And the reason I'm emphasizing this particular quantity is that it turns out that in the gravitational context, this particular quantity, these kind of entropies, very naturally are tied to the gravitational path integral. And so I'd like to already anticipate that. Now, what this requires us to do, the calculation of this thing, or the free energy, yeah, Z, yeah, so Z is another one, the thermal free energy. That would be the trace of e to the minus beta h, so it's a function. Well, it's not really a function of beta, because beta is not variable. Beta is fixed by the geometry, and we don't get to tune it, which is different from a black hole. But okay, at least, yeah, so, or for instance, this sort of thermal free energy. Yeah, or thermal partition function, okay? This Boltzmann partition function. So we could start asking questions like this to start to characterize the nature of rho hat. And well, like I mentioned a few times, it's a bit of a subtle problem because we have to sort of specify what we mean by the Hilbert space of field excitations localized in this region over here. However, I'd like to motivate a way to think about this object, which comes from the group theoretical analysis we did in the first part of these lectures, which was that, well, we could try to sort of put one layer of abstraction into the story and say that, well, this appears to be related, of course, well, this appears to be related to a different trace, if you remember, which was this Harishchandra character type trace that I wrote down earlier, where we were tracing over the content of a particular irreducible representation of the de Sitter group, yeah? And we wrote down very explicit expressions for this. And in fact, we managed to do this without spoiling the de Sitter symmetries. Quite the opposite. This was a result of the de Sitter symmetries, yeah? And so perhaps to connect the two, since we argued in the QFT portion that the state space of the QFT is partitioned into these irreducible representations, and we have expressions for the trace in a given irrep for these Harishchandra character formulas, maybe we can motivate a proposal for the partition function, yeah? And so there we should envision that the static patch Hilbert space, so let's do it for, again, for a free theory, just to keep our bearings in check. So for a free theory, we can imagine that the Hilbert space is partitioned into the set of single particle states, yes, and then the set of all multi-particle states. That's the natural organization of a free theory. And what this character formula over here, which is convenient to write in terms of, if you remember this density that I wrote down, Yeah. What we may be motivated to do is say, well, if this rho codes the density of states of the single particle Hilbert space, which is what IREP furnishes, yeah, and the multi-particle Hilbert space is just a kinematic factor that takes into account that you have the action of multiple sort of creation operators. We may motivate a definition of this thing sort of spectrally in the following form. That log z, so I'm going to write down a sort of proposed. Yeah, so take a free quantum field theory in the representation lambda. Right. And we'll write down the following. Yes. The following object. Okay, where beta is the de Sitter, where beta is the de Sitter temperature. And what is this over here? Well, morally speaking, you should think of this as a product over all energy eigenstates of, yeah, our hopefully well-known formula for an ideal gas at finite temperature. Yeah, so this I hope is a familiar formula. That is the partition function of an ideal gas at temperature beta for some free harmonic oscillator of energy frequency omega. Now, it's a little complicated to talk about products over continuous variables. And in the static patch, the spectrum of the static patch Hamiltonian takes continuous values because of the infinite redshift surface that allows you to change the energy of a state in the static patch by a very small amount. This is the effect of the Rindler horizon, right? So if you have the Rindler horizon, you can always excite states by a very small amount because you have this infinite redshift surface. And so that's sort of the problem with trying to define these traces, is that you have a continuum, the Hamiltonian of the static patch has a continuous spectrum. You can excite waves very close to the Rindler horizon that only infinitesimally change the energy. So you have this continuum. And usually the treatment of this horizon involves things like adding a brick wall or some Dirichlet boundary condition that cuts the modes at some location close to the horizon. But in doing so, you typically break the symmetries of the problem. So here, instead, we're using expressions that preserve the symmetries of the problem without offending the fact that you have a continuous spectrum. But what happens is that we had to incorporate this density of states, rho. And so we have a proposal based on this group theoretic perspective for what this partition function of the static patch might be. Now, there's a caveat here, which is that I integrated omega. Omega takes values, omega being the eigenvalue of the Hermitian generator, real valued eigenvalue of the Hermitian generator H, which is the generator of the SO1, 1. It takes values of the whole real line, whereas for the partition function of the static patch, I only integrated from 0 to infinity. And the vision here is that the conjugation that maps H to minus H would map you from one static patch to the other. And so the omegas that are negative would be more naturally associated with this static patch. And so I've made a choice here in integrating over the positive omegas. Yeah, so anyways, this is a hypothesis that we would like to test somehow. And so what we've done is written a group theoretic expression. And we know what rho is explicitly because I wrote down for you, yeah, what these characters are, if you remember. So in 3 space-time dimensions, for instance, for the principal series, I had these characters over here. They're known, they've been classified. Okay, but certainly for non-fermionic exceptional representations, they've been classified. And so we have an interesting set of predictions for what this partition function might look like. Yeah. So this is log z thermal. Okay. I hope that's clear. It's really just a glorified ideal gas formula where we've used the fact that group theorists sorted out the content of a particular irrep, which we're interpreting as the content of the single particle Hilbert space of excitations in a static patch. Yeah. Now, what we would like really is to see if this formula, yeah, this is a very specific formula, and actually I'll write it. I'll do the Fourier transform to write it in a language t is not time. To write it in the following way. So this is just an exercise in Fourier analysis, noting the relation between rho and this function over here, which is a Fourier type relation. Right. So we have sort of a group theoretically inspired formula, yeah. And let me give you a reference if you decide that this is what you want to study. Let me give you a reference, and let me even give you a section within the reference, because you are not going to read this paper unless you have very good reason to. You should, but you won't. Section 3, section 2 and 3. Yeah. Okay. So we have, okay, so what I've tried to do, using and implementing all these group theoretic methods and interpretation of the Hilbert space, keeping track of which generator I'm dealing with, knowing that I have this thermal density matrix, therefore trying to get a thermal partition function, we've motivated a formula. And I'd like to cross-check this formula against an independent calculation to see whether or not this formula is a sensible formula. I should say already that it's a formal formula in that these integrals diverge, as they should, because we're dealing with an ill-defined operation of splitting and breaking up Hilbert spaces at points and whatnot. So there's a question of whether there's a way to regularize this formula that is sensible, A, and that where the divergences can be interpreted in a covariant way. That may or may not be the case. And secondly, whether there's a sense in which we can generalize this kind of formula to the gravity problem. Yeah? So this is where we're at. And so what could be the way to proceed? Well, the way to proceed is as follows. When people study quantum mechanics and quantum field theory at finite temperature, they often calculate the partition function not only in a Hilbert space type of approach, but in a path integral approach, yes? And there's, fortunately, this was covered in Tarek's lecture. So the idea is that at quantum field theory at a finite temperature beta, yes, the thermal path integral in general is given by path integrating over all the fields of the Euclidean action, yeah, on a manifold where time is a circle, space, let's say, is an S3, and the circle has size beta, yeah? So this is an important result in thermal physics. And you can derive it again by remembering that the path integral computes transition amplitudes, and that trace e to the minus beta h looks like a time evolution in Euclidean time, and the trace causes us to identify the initial state with the final state and integrate over it, resulting effectively in this formula over here. Yeah, and so we may be inspired then to try and derive or write down a thermal path integral for the static patch. Yeah. After all, we noted that the static patch in Euclidean signature has a periodic time. So maybe what we should be doing to compute from a path integral perspective the thermal partition function of quantum fields in the static patch is to compute the quantum field path integral on the Euclidean static patch. Yeah. But the Euclidean static patch, we just argued, is the sphere. Yes? This object over here with tau, this object over here with tau periodically identified is a positive curvature for space, four-dimensional space, which is maximally symmetric and complete, because psi at 0 caps and psi at pi over 2 caps. There's no endpoints in this manifold. And if you're not convinced by that, you can compute its volume and confirm that it's the volume of a four sphere of that given curvature. Yeah? So this is a slightly non-standard metric on the full metric on the four sphere. And so we have an interesting formula that we may wish to understand, which is, well, maybe this de Sitter object, what did I call it? Z thermal de Sitter for the QFT, yeah, on a four sphere is equal to the Euclidean, and now we're doing QFT, so we don't have to deal with these Euclidean puzzles. This is well-defined, very well-defined operation, at least in perturbation theory, semi-classically. Maybe sometimes you can even define this path integral in lower dimensions. But we have the following formula, yeah? So rather esoteric-looking formula. Let me compute the four-sphere path integral of a quantum field theory, yeah? Kind of weird, in order to derive the thermal free energy of quantum fields in a rigid de Sitter background, okay? Now, and see whether these things have anything to do with each other. Okay, so that's our inspiration, and let's see where we get. Well, I'll start building for you the flavor of the derivation, just so for you to get a sense of it. And let's do a very simple example, which is, let's take a free massive QFT scalar. Let's have a mass mu squared on S2, just very simple, very bare bones, but it'll be sufficient to illustrate the point that we're trying to make. And, well, what is then the action? The action is the integral of the field on an S2. Yeah, so take your metric on S2, G, fixed, plus mu squared phi squared, yeah, minimally coupled to the S2. Okay, and we have this over here. That's our action, yeah, Euclidean actions. It's just a field where G is the metric on S2, round metric on S2, which is the Euclidean static patch, yeah. And, well, now it's a free theory, so there's a Gaussian integral. In this case, what we will end up is a functional determinant, yeah. Okay, functional determinant of the Laplacian on S2 plus mu squared. Yes, of course, there's some UV cutoff secretly in these functional determinants, because if not, we would have a dimensionful quantity, but Z is dimensionless. So even a free theory requires the introduction of a UV cutoff for these calculations. And now the question is, what on earth is this determinant? It's a two-sphere determinant. And so let's do some analysis of this determinant. And see where it takes us. Yeah? So what is a determinant? So let's take the log of this Z. So that's equal to minus 1/2 log det minus Laplacian plus mu squared over lambda UV. Yeah? And if we do a spectral decomposition of our eigenvalues, what should I use for eigenvalues? Gamma. So what will we get? We'll get a the degeneracy of a given eigenvalue gamma log times the eigenvalue itself of the Laplacian plus mu squared over lambda uv. Yeah, so formally speaking, remember these things diverge, but we'll discuss the regularization in a moment. I hope this is clear. Where what is gamma? Well, that's the set of eigenvalues. Gamma are the eigenvalues of the Laplacian on a two-sphere, which, okay, I hope is a familiar problem, but it's LL plus 1, where L takes values from 0 to infinity, and the degeneracy of gamma is 2L plus 1. Yes, it's our spherical harmonics. It's smooth functions, a complete functional basis on two-sphere, okay? And so this object over here, we're trying to test whether it has anything to do with this object over here. It looks nothing like it, but we'll proceed nonetheless. So, firstly, I'd like to implement a regularization scheme that's covariant for this thing. In other words, that the only type of divergences that it yields are divergences that can be associated to local counterterms of the background metric. So let's regulate using what's known as the heat kernel method. Regularization. So, and what I'm going to do is effectively replace the logarithm over there with a type of proper time representation, which will have a cutoff parameter, epsilon, over 4 tau. Yeah, times, well, so we will replace our logarithm on the eigenvalues with, with the following. So let me write down the formula and then I'll explain it. Yeah, so I'm summing over the degeneracy, but instead of having this log over here, which is very formal because as L becomes large, this is a badly divergent sum, I'm going to regularize with this epsilon cutoff, which has the effect of cutting off so the large eigenvalues, yeah, because when L becomes very large, you're driven to this small tau regime, right? So because L becoming very large, the part of the tau integral that is unsuppressed is the very small tau, but at very small tau, epsilon has the effect of damping the integral. So epsilon is a regulator, yeah? That's called the heat kernel regularization method. And so now we have at least a formally finite, a finite expression, and we'd like to understand the limit where epsilon goes to 0, yeah, of this expression, which is our regularized version of the functional determinant. And so let me give you now some flavors. First of all, one can proceed, and there are methods to proceed where you treat this problem in terms of its discrete basis, and there are many results known about these functional determinants. But I'm going to take an approach that's a little different in that I'm going to introduce yet another integral, and it'll become clear momentarily, I think. So I'll introduce another integral which has the property that allows me to complete the square of these quadratic functions in L. So let me, yeah, LL plus 1 tau. Actually, probably the units should be like this. But okay, let me work in units where L is equal to 1 to avoid making a mistake. And then we can reinstate units by ensuring that mu appears only with dimensional combinations with L. So we have mu tau e to the epsilon squared over 4 tau. Yeah, still a finite integral. 2L plus 1, L going from 0 to infinity. And let me get the factors correct. Because here I should look at my notes. Yeah. Almost. Yeah. 4 tau. Okay. And this over here, actually, because I completed the square, is a mu squared minus a quarter tau. Yeah. So these are all straightforward to derive steps. Yeah. And now, still have finite sums, finite integrals. Everything's finite. So let me give you a step or two more, and then I'll just declare the result. But just to give you a flavor of how one is manipulating these path integrals. So now I can actually do the tau integral. Firstly, since everything converges, I can safely move this sum into here. And now this sum over here is a geometric series, which is doable. Yeah. So I can sum over all the spectrum of eigenvalues. This gives 1 plus e to the iu over 1 minus e to the iu squared times e to the iu over 2. Yeah, so that takes care of that. I can actually perform the tau integral, although there's this pesky 1 over tau. It's actually an integral that can be done. It's not too nasty of an integral. And the result of integrating over tau yields the following integral in u. Yeah, where now I'm really working in terms of a regulated expression, so we good. Right, times this object over here. So nice calculation. Good, yeah. We're new over here, I should say. I've defined to be the square root of mu squared minus 1/4. Okay. So these are steps. Okay, you can go over them afterwards. And finally, there's one more step that one has that I'd like to do, which is change variables from u to t to it, and do a contour deformation that does not go over any poles. So this is full of poles, and there's a branch cut. So please ensure that when you do your contour deformation, you don't cross the branch cut on any of the poles. I want you to wrap around the branch cut, okay, because of the square root branch cut. And the resulting expression, the resulting expression when you wrap around the branch cut at stop at the branch cut where t is equal to epsilon, yeah, takes the following form. Now this is a little bit of detail, but I wanted to show it to you to show you how something as peculiar as the product of all the eigenvalues of the Laplacian on a two-sphere might start to resemble. And this was, when this calculation was done, it was completely unanticipated. We didn't even know what Harish-Chandra characters were. So I'm giving you a logic that's reverted from the derivation. Sorry, and this over here is t squared minus epsilon squared. Okay, so we have the following object over here. Yeah. So I've given you, I think, sufficient steps to get a flavor of how one might land on this very unusual looking expression for the functional determinant on a sphere. But the steps can be followed essentially in any dimension for any mass. for fermions and higher spin massive fields. Gauge fields require a little bit of care, but the story, the type of manipulations carry through as well. But what has happened here is that we've landed on an expression for log z, which is regularized in a covariant way. It happens to this yeah.
If the mass is tachyonic, we can still write this.
No, if the mass is tachyonic, this is ill-defined from the get-go because you have a blowing up at tau goes to infinity. And so you have to now decide what you're going to do about that infinity. Yeah.
Okay, thank you.
Even when the mass is 0, you have to deal with a 0 mode. Yeah. So what you may want to do in that case is keep in the sum only those L's that are larger than the mass, and treat the 0 or negative mode sector separately. Yeah? So here we're doing the, anyway, so the standard massive case. And what has happened, I erased it, but is that if you formally set epsilon to 0, yeah, you landed precisely, so this over here is the two-dimensional character for lambda is a half plus I nu, yeah, where nu is this square root over here. One landed precisely on the character formula that we anticipated based on this naive group theoretical reasoning. And I think when I wrote the formula previously, I may have missed this factor over here. That's a typographic error. So what has happened? Yeah, or if you want me to go back to the frequency basis, we've landed on this ideal thermal gas formula over here. Okay? So we've accomplished a few things. One is we never had to offend the de Sitter symmetries in regularizing our problem. We didn't have to put brick walls anywhere that would break the symmetries. We did this in a way that respected the symmetries of the problem. Secondly, we've regularized in a covariant way, so we know that although this expression diverges at epsilon going to 0, the structure of the divergences are governed by the presence of local counterterms in the quantum field theory and nothing more. And so the divergence structure of log z will take the following form. I can write it down for you. Yeah, so limit epsilon goes to 0, log z will have, so epsilon is related to lambda uv, I think roughly as there's a precise coefficient, but let me not remind it now, roughly in the following form. We're going to have a structure that has a divergence 1 over epsilon squared times the integral of the metric. That's the leading UV divergence of the functional determinant that you could view as renormalizing the bare cosmological constant. And then we'll have another divergence, which is the other local term we can build out of the metric, which you can view as a term that renormalizes the bare Newton constant if we couple the theory to gravity. And finally, there will be a logarithmic divergence, log epsilon, which has to do with anomalies, usually in the case of conformal field theories, things like the conformal anomalies, and this will only occur in even space-time dimensions. These are these logarithmic divergences, and it has to do with the fact that there's another local counterterm that we can write, which is, sorry. I was working in higher dimensions. In 2D, the divergences that we have are this divergence. The other local counterterm would be the Gauss-Bonnet invariant, but this has a dimensionless coefficient, and when that happens in quantum field theory, these counterterms, the coefficient of this counterterm gets renormalized by a logarithmic divergence, because when we rescale our cutoff, we change the overall number. And so the divergent structure of this formal expression we wrote down previously is clear, it's covariant, and it shows, as it should, that the expression is indeed infinite. However, the infinities from this Euclidean path integral point of view can be absorbed into physical couplings if we couple the theory to gravity, because we have a Newton constant and we have a cosmological constant, and precisely the bare values can absorb these things over here and get renormalized. Yeah? So this path integral approach to the thermal partition function of the static patch is a particularly interesting method. Yeah? So what has happened right now is that we have, out of something quite esoteric, which is putting the quantum field theory on a featureless sphere, which has no thermal cycle that's non-contractible, actually, which is a very big distinction from quantum field theory, where thermal quantum field theory has a structure of S1 times S3. Here, the S1 is living inside of the S4. We've managed to write a quantity which we seem to have a thermal interpretation for, okay? Where beta, I remind you, is the de Sitter temperature inverse, okay? Now, let me pause for a moment and see if there's any questions, because a reasonable amount has happened.
Can repeat the difference between the thermal QFT in...
So standard thermal QFT, imagine you have a QFT that lives on some time direction times a 3 manifold. Let's take it to be S3. Yeah, we have R times S3, and we want to put this at finite temperature. What we would do is we would take R from Lorentzian to Euclidean and wrap it around in a circle. But this is a product structure. This manifold has a product structure. There's an S1 at every point on the S3. Yeah? Because of the curved nature of the de Sitter space, when we continue the static patch to Euclidean signature, instead of there being an S1 times something, it got subsumed as a circle, a contractible circle, inside of the S4. Yeah? So the static patch S1 in the 2-sphere is the maximal circle of S2, but it's a circle that can contract to a point. Yeah? So it's of a different nature. And this will come back to bite us in a moment. But is it clear? There's no product structure. S4 has no non-contractible one cycles. Okay, yeah.
The first,
Betty numbers. Yeah, what?
I can imagine the first like an figuration, and the second one not.
The first as?
A figuration.
Like yeah, that's right. Yeah, that's right. So so this is sort of somehow more trivial topologically. Okay. This thing. Yeah. Okay. So, any more questions? Very good. Let's proceed then. So essentially, what it appears to be opening is an avenue where we can study properties of rho, at least thermodynamic properties of rho, like its trace, by employing Euclidean methodology. And this was at the level of QFT. And we got as far as we can conceivably get, which is a formally divergent quantity, however, where the divergences now can be understood in terms of local counterterms. And the thermal character is interpretable in terms of these Harish-Chandra group theoretic traces, which is useful because we have a trace interpretation of this formula, which is rare. So that allows us to proceed. Now we'll make another conjecture. So that's good news. Yay. And now we can say, well, what about, and I should say, at the interacting level, there will be a Challen-Lehmann type expansion, like there was for the 2-point function for the z, where we have to further sum, just like we had interacting 2-point functions that we could expand in a basis of free Green's functions. Similarly here, we may be able to expand this in a basis of the free partition function. So these are really significant building blocks of the problem. So now we can do this exercise for spin 1/2. It works. we get the analog Harshchandra quantity. And now we can do the exercise for massive spin particles higher with massive, well, let's do integer spin for now. Particles that have higher spin. And something, you know, so we would conjecture similarly that for any theory, we associate a particle with its irreducible representation. We take our math books for Harishchandra characters. They've been written down, especially for bosonic spin. And we say, well, you know, you tell me your representation. It's labeled by some lambda and some spin part of the SO3 subgroup. The Casimir in 4 dimensions would be lambda 3 minus lambda plus SS plus 1. Yeah? And we may want to declare that the result of the sphere path integral of these higher spin massive fields yields the following quantity. Yeah? So just in exactly the same spirit that led us to this formula over here, and if we wish to have the regularized expression, we replace the t's with square root of t squareds minus epsilons in the appropriate locations. However, again, much to one's surprise, this isn't quite the right story, because when you compute the sphere path integral, and this I will only claim the result, but it has to do with the fact that when you try to formulate as a local quantum field theory fields, massive or not, with higher spin than 1, you need to introduce gauge fields. This is known as the Stuckelberg mechanism in the case of spin 1 and higher, and for massless fields, they're gauge fields, and so again, you need to introduce a gauge invariance and BC ghosts to deal with it. Yeah.
Do you see the difference between light and heavy fields here?
No, so complementary and principal series follow the same pattern, but gauge fields have additional zero modes that one has to be careful about, which I'll discuss in a moment. But let me first discuss the slightly easier case of massive higher spin fields. And what happens in that case is that this formula is almost correct, except there's a correction. There's a correction term, which is a character, in fact, so if we're in 4D de Sitter, this is a character of SO4,1. So there is a corrected character which takes the form of an codimension 2 de Sitter group. Yeah. So it yields a smaller divergence. So just for you to keep track of the divergences happen when t goes to 0. That's the regime where you have divergences. And what you get is a rather curious feature that the naive character representation appears to have a bulk contribution and what one may wish to call an edge contribution, in the sense that the UV divergences that this edge contribution gives rise to look like they live on a codimension space, codimension 2 space, which would be almost like the dimension of the horizon. Yeah, that's an interpretation that comes purely for analyzing its divergences, but I can tell you as an aside that people that study entanglement entropy for gauge fields often find that this is partitioned into what's the word that they use? An extractable entropy, which has to do more with the bulk part of the operator algebra, and an edge type entropy that has to do with localized physics at the entangling surface. And when one can compare to that literature, for instance, for the Maxwell field, which is conformal, and you can place it on S4 and compare to existing literature, the contribution of the logarithmic coefficient divergence of the entanglement that was written down and announced in that literature matches the contribution that comes from here. So, and perhaps this is to be anticipated, that we should have only claimed that our formula is true up to edge corrections, because we split space precisely on a codimension 2 surface. Yeah? And it would have been almost too much to ask for that there would be always a vanishing contribution to the thermodynamics from this codimension 2 surface over here, okay? And so if we take seriously the method of the sphere path integral as a computation of this z, and the reason to take it seriously is that it preserves the symmetries. We can calculate it in a covariant way. It admits a loop expansion that's under control. We understand its divergent structure in terms of the bare couplings of the theory, coupled to gravity especially. Perhaps we should take this formula seriously, okay? In fact, in a sense, it's the only reasonable formula that one can write down for the kind of question we're asking, especially if we don't introduce extraneous data like an operator that lives along the whir line that we can use to define a Lorentzian type of trace in the theory, which is this paper I mentioned moments in the last lecture. Yeah? So that's the situation. And so what I'd like to push forward is this quantity over here as a proxy, or the definition, perhaps, of what we even mean by this thermal partition function. And note, another feature that's convenient or interesting is that from the point of view of Z, we never had to cut our space anywhere. Yeah? It was a calculation that was done on a closed space, and I didn't need to confront the issue of where is the location of my cutting surface, and that, when we're dealing with diffeomorphisms, is a very useful thing, okay? And so that's another advantage, that I don't need to tell you, oh, it's here, if there's a gravitational fluctuation, I have to define an operator for the position of this thing, take its VEV, and so forth. All right, so now let me tell you what happens in the case of gauge fields, just to complete the story for you. And along the way, actually, in doing these calculations, we uncovered, fun fact, some characters which it's not clear to me had been computed before. And so there's, you know, in the worst case scenario, this produced some fun results. But maybe they had been computed, but anyways, we can produce them rather efficiently. Now, for gauge fields, which are the discrete and exceptional series representations, the computation had the above structure. The result of the calculation, which I'll just state for you, has the above structure, bulk and edge splits, including for the graviton, I should say. So if you calculate the graviton, there's an edge split as well, which predicts something about the character of edge modes of the gravitational field, which is an important open problem. But there was an additional contribution, which, so let me assume that I have a gauge theory whose gauge coupling is given by gamma, yeah? So that's the gauge coupling. There was an additional contribution, and let me assume that the gauge group G has dimension dim G, yeah? There was an additional contribution which went like dim G over 2 log gamma, okay? So there was a term that contributed to the sphere path integral in a gauge theory that was sensitive to global properties of the gauge group, curiously enough. And the reason for this is that when we calculate the path integral of a gauge theory, we have to divide by the volume of the gauge symmetries, the gauge group, because if not, the path integral would be infinite, in other words. So generally speaking, Z gauge is equal to some path integral, for instance, of a gauge field, e to the minus the Euclidean action of the gauge theory on an S4, but we have to divide by the volume of the gauge group, G, the full local volume of the gauge transformations, which is an infinite number of transformations. And what happens is that in doing this path integral carefully, there's a residual term in this path integral from the constant part of the gauge group that survives, and you have to normalize the volume of this group appropriately as dictated by the locality of the theory. And that gives you that the volume of the group should be measured in units of the coupling. And so this is where this formula comes from. And so we have yet another feature. Now, this feature is even more puzzling than these. Say that I offer you at least this vague or schematic notion of this as being an edge mode. Here we have some new contribution to the entanglement or the entropic structure. But remarkably, there's at least one context in which this has appeared that carries an interpretation, and the context is topological quantum field theory. So this is another aside. So if you calculate the entanglement entropy, this is just an aside, this is a fun fact. For topological quantum field theory, like Chern-Simon's theory placed in a 3-sphere, and if you calculate this entanglement entropy, when you quantize the theory in a 2-sphere times time, you get terms that are indeed sensitive to the gauge coupling of the theory. Yeah? So that's just an aside. You need to, it's just an aside in case that you've studied topological quantum field theories. Now, where does all of this take us? Yeah, just to go back to the main storyline. Yeah, is that in trying to understand the properties of this row, yeah. There's 1 hour left? There's half an hour left. Oh, okay, let's see. I think I can wrap up. But what I think one should take out of this discussion is a proposal that is worth studying for what we might mean by the gravitational analog of this the sort of thermal partition function that we computed in QFT. And I think it's very well motivated to try to do it in gravity, in that the QFT calculation was infinite. It had divergences. But the divergences, if the theory is coupled to gravity, as we considered in this work, are naturally absorbed into the additional couplings of the theory, because you see now you have the bare cosmological constant and the bare G Newton, and you can absorb these divergences, these are local terms, into physical couplings, which then you measure. And so these are no longer ambiguities, rather they're an indication that you have to specify and measure the couplings of your theory. Yeah? So adding gravity to this quantum field theoretic Z actually makes it better defined. A theme that has been, that reoccurs in the literature when it comes to questions of these type of quantities, and this was something that was certainly pointed out in this paper. And so then, what is it that we would like to think about? Well, maybe what we would like to think about is a gravitational path integral that, with all the caveats I already talked about in Euclidean gravity, yeah? So I'll suppress the matter contributions, but they're there in principle as well, yeah? That maybe the trace of this rho, yeah, in a gravitational theory is given by the gravitational Euclidean path integral, yes, over a compact, a closed rather, 4-manifold, like the 4-sphere, yeah? So let's start with the 4-sphere, okay? So we have a closed manifold. I haven't specified the metric on the manifold, but I've specified the topology, and I'm specifying that it's entirely closed, okay? And the action, well, this can be a general effective field theory, but let me start with just the Einstein action just to exemplify the problem, yeah? So we have this over here. And maybe the quantity, semi-classically, in quantum gravity that calculates this partition function is given by this object over here. Now, what are the benefits of this object? A, like I said, I don't need to specify the location of any surface. It's an intrinsically diffeomorphism invariant, calculable, systematically calculable quantity that admits a systematic loop expansion, yes? It's field redefinition invariant, so it already satisfies properties that no Lorentzian observable that we know of in de Sitter satisfies. So it's invariant under local field redefinitions because I'm integrating over all the metrics on a closed manifold, yes? So local field redefinition would just be accompanied by a Jacobian that would render the output of the integral the same. It's like doing a change of variables in an integral on a closed space. And at least in the sense of the saddle point approximation, we can study it systematically, yeah? So we have an object that appears to be, in light of all of the subtleties, a rather a curiously well-defined, let me not call it observable, but a curiously well-defined calculable quantity, yes? And so this may be an object that we wish to study, okay? Good. So now let's explore what this thing is by doing the simplest conceivable calculation, which is the saddle point contribution in the dominant saddle, yes, of this theory in pure gravity. So what's the situation? Well, remember, in the saddle point solutions are solutions that satisfy the Euclidean Einstein equations, yeah? Euclidean Einstein equations. So any on-shell saddle, any saddle will have a Ricci scalar that's equal to 4 lambda. And so the on-shell action of a saddle will be equal to 1/16 pi d4x root g minus r plus 2 lambda gives, what does it give? 2 lambda minus 2 lambda? Minus 2 lambda. Yeah, so this is then for the volume of our space times lambda over 8 pi g. Yeah? Okay? Good. Good. And the saddle, well, so it so happens that there's 4, if you can ask a mathematics question now, it's in the space of compact enclosed 4 manifolds, what is the Einstein space? So this is called an Einstein metric. Any metric, so this implies that R mu nu is proportional to G mu nu, yeah? And so these are called Einstein metrics. Those Euclidean smooth metrics that solve this equation are known as Einstein metrics, and the manifolds that support Einstein metrics are known as Einstein manifolds. And we can ask, what is the Einstein manifold with the Einstein metric that has the largest volume? And that is the round force sphere. In fact, the only Einstein metric known on the topological force sphere is the round metric on the force sphere. A priori, there could have been other ones, but it's an open mathematical problem whether there exists other Einstein metrics on the force sphere. But certainly there's the force sphere, and it's the roundest one, and it's the one with most symmetries, even compared to other Einstein manifolds. So this is the largest symmetry. And its volume in the units that we're working in, if I remember correctly, is 24 pi squared over lambda squared. Yes, it's a 4 volume. Lambda has units of 1 over length squared. Okay, so now let's compute the on-shell action. So we have, what happened to lambda? Oh yeah, lambda 8 pi g. Notice that this is positive. Yeah? No, negative. The action is negative. Yeah? So the on-shell action is minus lambda over 8 pi g times 24 pi squared over lambda squared is equal to 3 pi squared over, 3 pi over, minus 3 pi over lambda g, okay? Yeah? Minus 3 pi over lambda g, and so, we end up with the following approximation, e to the minus SE classical, which is e to the 3 pi over lambda g, where I've set units h bar equals c equals 1. And so we have this quantity, 3 pi over lambda g. Interesting quantity. It's a dimensionless quantity that we computed in this Euclidean methodology. Notice that we had e to the minus the action, so this became a plus. And, well, let me write this. So let's remember now that lambda is equal to 3 over L squared. So let me write this as pi over pi L squared over G. Yes? Or let me write it as 4 pi L squared over 4G. Oh, good. But now, what's 4 pi L squared? 4 pi L squared is the area of the de Sitter horizon, curiously, over 4G. Yes? And we might as well add in the factors of all this G Newton. Let me write it down with all of the quantities. Pi L squared C cubed over G H bar, because it's a nice formula. This is a formula that contains within it the coupling constants of cosmology, relativity, quantum mechanics, and gravity, all in one package. Quite nice. And it is A over 4G, yes, which if we are to interpret log Z as a free energy, which is equal to S minus E over T, we would say that, well, this over here is related to some sort of free energy. But we should remember that in gravity, as I kept on emphasizing, on a space with no spatial boundaries, the energy is actually zero. Right? There was no, the matter energy is canceled by the gravitational energy, and so there's no spatial boundaries, and so it's conceivable that what is happening here is that log Z, thermodynamically interpreted, is just a pure entropy, and, well, we computed its approximation to leading order, and we got A over 4G, which is a formula that's rather familiar from the Bekenstein-Hawking expressions of black holes. I didn't start with A over 4G in this discussion, but somehow I landed on it from this point of view, and I landed on it in a way that I can systematically compute corrections to it, because this is just the leading order approximation of a sequence of terms, yes? And so let me give you a flavor of the corrections. So for instance, let me give you what it would look like at one loop, yeah? Because now we can calculate at one loop this object, which I'm going to call the partition function of the universe to avoid interpreting it as an entropy. So I won't call it the quantum de Sitter entropy. That's what people often call it, but we can certainly call it the partition function of a universe. But let me just give you a flavor of what it looks like. So to leading order, it has this 3 pi over lambda g. The next to leading correction is related to these group volume factors I discussed. It's 5 times log S naught. So let me define this quantity to be the tree level value of S. And then there's a term which comes from the Harish-Chandra logic, which I'm formally setting epsilon to 0. But there's a chi for the S is equal to 2 discrete series. So delta is an integer. In fact, delta is equal to 3. Chi bulk minus chi edge. Yeah, and the chi edge, I believe, involves SO2, 1 discrete series in delta 1 and delta 2. Okay, so we have this quantity over here. The divergences are such that are absorbed in the physical couplings lambda and g. So I no longer have an infinite quantity. I have a renormalized quantity, which is a different concept. And finally, there is a term which comes from the fact that the Euclidean path integral is unbounded, and we have to complexify the contour of path integration, and this picks up a phase which was first computed by Polchinski in a nice paper. I think I have that reference too. Let me find the reference. Maybe I don't have it written down here. But it's a bit, well, you can find it in the paper. We call it the Polchinski phase. It was anticipated in an earlier work of Hawking, actually, but Polchinski sorted it out. And the phase in four-dimensional Einstein gravity goes as, so z goes as I plus or minus I to the 6. Yeah, so that's what e to the plus or minus, what is it? I pi, 3I pi. Is that what it is? Plus or minus 3I pi. Did I get it right? Something like that. So there's a phase. There's a phase that appears in the de Sitter calculation that doesn't appear in the black hole calculation because of extra zero modes in the path integral when we do these contour rotations, and because the manifold is closed. Had the manifold been open, had we added boundaries to the manifold, we would have changed the boundary conditions and pieces of this phase would not be present. But the phase should be taken seriously if we're going to take Euclidean gravity seriously. Okay? So that's the one loop structure of the partition function, the de Sitter gravitational partition function in all of its details in the heat kernel regularization, and one could in principle continue going. You would produce a set of local UV divergences and a set of terms which would be more non-local and therefore less ambiguous, less subject to counterterms. And one can add matter contributions as well, so then we would start having these Hirshhandler characters for more and more configurations. And so we have some sort of building blocks. Okay, how much time do I have left? 1:05. So, oh, good. Then I'm going to end with, okay, so let me pause to see if there's any questions. So what, yeah. Yeah.
One comment I forgot to make. Dio is fluent in Spanish, so if you're thinking that English perhaps is stopping you from asking some questions, drop it and ask it in Spanish if you know Spanish.
Correcto.
Yeah,
but not in
unfortunately,
Portuguese.
I'm not fluent in
Yeah.
Spanish, so let's go. So here what you're doing with the saddle point approximation is, in some sense, you're choosing a background metric, ds, and you're doing perturbations over it to compute the...
A saddle point metric, yeah. So it's a saddle point methodology. So we're looking for, I'm using the saddle point approximation, and the saddle point approximation is an approximation that makes sense in the limit where g lambda goes to 0. So that's the regime in which the action has a large coefficient, and so I can implement the saddle point, and then the corrections will be suppressed by this quantity. That's the idea. So it's not choice of background metric as much as it is a saddle point method. Yeah.
Hi, just a brief question. So what's essentially the difference between the saddle point approximation and the supersymmetric localization? Because it looks very similar.
Yeah, the supersymmetric localization relies on the existence of a nilpotent operator that I can use to deform the action and then drive it there, and it often yields results that are, in a sense, one loop exact. Here, there is no analog of that nilpotent operator in general, and in general, the results will not be one loop exact. It's an interesting question, nonetheless, which I've tried to explore, whether we can find modifications of this theory that are subject to supersymmetric, or something analogous to localization where we can calculate it exactly. So the question is inspired, in a sense. Yeah.
Okay. Yeah, because it looks similar in some sense, like the thing localizes in certain points, and you.
Yeah,
at a
that would be
term it
nice.
goes to
Maybe
zero.
maybe it even localizes at the horizon. But these are very. I don't have. I've tried, but I failed. Yeah.
Thank you.
If you want a reference, there was a paper I wrote with Beatrix Mullman and Pietro Benetti Genolini called DS2 Supergravity, where we tried to proceed in that direction. Yes. Could some, the archive number is, can someone, okay, let me continue and then someone can, yeah. Well, maybe okay. And Mullman. Okay. Okay, now I'd like to say, I would like to end on a sort of broad scope note. Yeah, 2309.02480. Yeah, that was an attempt. Maybe this attempt can be. One of the issues with localization is that sometimes the localization pattern has boundary terms in the configuration space, because it's like integrating a total derivative. And what seems to be the case is that in the model we studied, there were boundary contributions and there's less control of those terms. Yeah. Okay, so good question. Very good question. So, good. Okay, now, I'd like to end with a general remark that is a part of this paper and, in fact, another paper. So now we're really reaching a more recent literature. So the other paper is 11330. So just fairly fresh paper. And the question, okay, so there's a lot to understand. In fact, this phase is an open problem that we should understand. The fact that we have no thermal circle suggests that it's integrating over all thermal cycles, which is like sometimes what we do when we go from the canonical to the microcanonical ensemble, where we take Z of beta and we integrate over all beta. So this might be the reason why Z is actually more like a microcanonical calculation. So there's a lot to understand, but I'd like to emphasize a bigger question and a bigger issue, which is that in effective field theory, we have a lot of information that comes with our theory, which has to do with the specification of all of these physical couplings. Yeah, so we expect in effective field theory that there isn't just the G Newton and lambda, but there's all these physical couplings, and similarly for matter fields and so forth. Yeah, so and it better be the case that we have a way to invariantly define, sort of in a gauge invariant, field redefinition invariant way to define what these physical couplings are. And in the S matrix, in a sense, serves as this role because the S matrix is a truly gauge invariant field redefinition invariant quantity, and we can use the S matrix elements to define this infinite string of physical couplings, yeah, in our theory. And similarly for boundary correlators in ADS. And so we have a rich enough data set of observables to define for us this rather large physical data set of coupling constants in effective field theory. Yeah? So this is an important point, that observables are not just nice to have, they're necessary to even specify what we mean, because writing a Lagrangian with couplings is not a particularly invariant thing. If I field redefine my metric, yeah, how to some other sort of tensor spin 2 object that someone else may decide is their metric, yeah, this will reshuffle around all of these couplings, yeah. So these couplings are not really in a Lagrangian formulation of effective field theory are not really truly invariants. They're sort of ambiguous. We haven't defined what we really mean by them. And physical observables are the way we really define physical couplings in a physical theory, yeah? And like I said many times, we don't really have asymptotia or an S matrix as cosmological observers. This is troublesome, not only in a philosophical sense, but in a very practical sense, that it's not even clear at the level of effective field theory what we even mean by the specification of our theory. What is the invariant data set, the invariant theoretical data set that's truly diff-invariant, field redefinition invariant, physical, that we use to specify what we even mean by the effective field theory? Yeah, so this is a very grounded, relevant question, because we say, oh, we can calculate stuff here. That stuff, A, is out of causal contact with any experiment we can do. B, it specifies things like points or momenta, which are not particularly diff-invariant. C, they're specified in terms of values of fields, so they're field redefinition dependent. These are not really invariant quantities. Of course, if we exit the universe like an inflation, then we have some other quantity and relational quantity, and we can define them like that. But if we're truly cosmological observers, sitting inside this world, trapped in a finite portion of space-time, we're trapped in a region of space-time where we do not have the type of rich data set that we would in an ordinary theory. So we either have to live with the idea that these will always be prone to error, that we can only define physics with a given tolerance, and that there's just no such thing as this theory. It's just some rough, hazy meaning, or it could be that the data set is there, it's just coded in a rather different way. After all, not all physical theories that we have are theories with an S matrix. And I go back to this example of topological quantum field theory because I like that theory, because that's a theory with no local operators, no S matrix, yet it has a very well-defined meaning. In fact, it's the most well-defined quantum field theories that we have. So similarly here, I think it's important, not just aesthetically, but practically, that one has identified objects like this partition function that are truly invariant. Now the question I'd like to end with is to give you a flavor, to give a sense of how much could this code. And so the rough map, and so since these are the final comments, I'm allowing myself to be dreamy, dreamery, whatever the, and so, but the point that I want to make is that for the S matrix, we have a notion of the on-shell observable, the physical observable that we use to physically specify, since that's the measurable, the coupling constants of nature. And here, perhaps we should replace the notion of an on-shell matrix element with something like these saddles, yeah, that we fluctuate around. So this on-shell, like this S4, right? It's a semi-classical, rigid thing that we can use to define, if you will. So G and lambda are couplings that we define through the action. But if we define rather in the regime where G lambda goes to 0, their meaning in terms of log Z, yeah, this log Z is an invariant. And so maybe what we really mean by lambda G, which is coupling Lagrangian-based physics, is better stated that this is what the role of log Z is to define those particular couplings. But then it better be the case, if this reasoning makes sense, that there's a rich enough information in this Euclidean path integral to define what appears to be a very large number of physical couplings. And so we can ask the question, what is known, even at the settle point approximation? So, what is known about the content? Sorry, there's a log missing over here as well. What is known about the content of this path integral beyond the sphere? Yeah? So it's a mathematical question. In other words, what is known, what do mathematicians know about the space of closed four manifolds, which are Einstein, yeah? Einstein four manifolds. And how many are there? And how many Einstein metrics on these four manifolds are there? Yeah? So this is a remarkably with not too many steps of abstraction, we've started with a question, a physically motivated question for cosmology, and landed on a question which has to do with algebraic geometry and topology, yeah? Which is perhaps an interesting thing. So I'll just declare the result in 4 dimensions. So Einstein metrics which further have positive curvature. Yeah? So Einstein metric, remember, is a Ricci tensor proportional to the metric. And positive curvature, it's guaranteed to have constant Ricci scalar, but positive curvature means that this is, yeah? So this is a restriction on the space of 4 manifolds, because many 4 manifolds are vanishing and usually negative curvature. So this is a rather restricted problem. And think about Riemann surfaces in 2 dimensions. Most Riemann surfaces have negative curvature. And then there's only one which has a sphere. So it's, you know, hopefully the answer is there's just a 4 sphere, nothing else. Hopefully that's not the answer. But okay, so what is known? This list is not complete. It's just a known list. So now let's fix the topology to be S4. On S4, there is only known the round metric on S4. It's an open question in mathematics whether there exists other smooth Einstein metrics on S4. Pick your favorite mathematician, ask them what they know, but it's just the round metric on S4. What we know is that small perturbations around S4, it's isolated, so there's no moduli space here, there's nothing nearby, but there could be some bizarre, non-isometric, smooth space on the topological S4 that is there. We just don't know it. So right now, it's just the S4. So that's a fairly empty data set. However, there's a known metric on an S2 times S2 manifold, yes? So again, 1. There is a known metric, Einstein metric, this is sometimes called the Page metric, on a fibration of a 2-sphere around another 2-sphere. So this is not quite a simple product of 2 spheres, but rather a 2-sphere that's fibered around another 2-sphere in a smooth way. So there's a known metric on that. Again, just 1. There's what's known as the complex projective space, CP2, which emits an Einstein metric, which is known explicitly. It's a Fubini-Studi metric. Okay. And finally, there's a class of metrics which are known to be sometimes called hashtag manifolds, sometimes called Del Pezzo surfaces. And I'll just tell you what they are. So you take a CP2, which is a particular compact manifold, which topologically has 1 2-cycle inside of it, and it's a fairly regular metric. In fact, it has a lot of isometries. And you remove from it k points at generic positions on CP2. So you sort of remove k points, excise a little region around k generic points, and you do an operation that mathematicians call blow up in these points, which is sort of to open them up a little bit, and glue to that another CP2 whose orientation has been reversed. And so this is called a connected sum of 2 manifolds at k generic points with blow up. And these metrics are known, and the range of k actually is restricted. It's from 2 to 8, and it's also known that for k is equal to 2, 3, and 4, the metrics are isolated. Again, there's only an isolated metric on each of them. However, for k, 5, 6, 7, 8, there's known to be a non-trivial moduli space of metrics. So there's a continuous family of Einstein metrics that live on this k is equal to 5, 6, 7, 8, that give you an infinite continuum of Einstein metrics that you can play with, okay? So that's the good news. The good news is that if you take seriously all the saddles and all the Einstein manifolds of this path integral, you end up with a moduli space of Einstein metrics, yeah? And that's good news, because perhaps you have a rich enough invariant data set to counter your a large number of physical couplings. However, I will end with a caveat, which is that of all of these, only 2 admit a canonical spin structure, which is to say that only 2 allow neutral fermions to be placed on them. Having said that, the remaining ones admit what's called as a generalized spin structure, or a complexified spin structure, which means that if your fermions carry a certain charge, then you can place them on these manifolds. And it turns out that there is a charge in the standard model. So you may ask, can I put the standard model on these manifolds? Where you should be asking this question. And it turns out that if you gauge the one non-anomalous U1 global symmetry in the standard model, which is the U1 associated with the difference of the baryon number and the lepton number, the fermions of the standard model carry precisely the required charges to be able to be placed on these non-spin manifolds because they have this spin structure. And so maybe, maybe there's something to that, because we would very much like to have all these manifolds to define all these couplings. Or maybe there's other manifolds that we haven't discovered yet. But you see that very quickly, if there is a consistent theory for these lambda positive worlds, and if it makes sense at the quantum level, there really has to be an invariant data set that can accommodate the physics of effective field theory. And that's not actually a simple requirement. That's a stringent requirement that is taken care of in Minkowskian physics and anti-de Sitter physics. And so we may have to, in order to answer this very mundane and well-grounded question, we may have to go to rather exotic places. However, it seems to me that we should not take lightly the existence of these kind of invariant quantities. And maybe the information content is coded in this rather non-S matrix type way, but is coded in this Euclidean structures. Okay? So I think I'll end it with that. Yeah, we've covered a lot of ground. I was a little quick and sketchy at times, but there's a backup behind all of that and within the references. But I wanted to end with a very sort of grounded physical point. Okay? Good.
Okay, questions for Leo? Yes.
So from the last thing that you mentioned, what do you mean that happens geometrically for a manifold to admit a spin structure?
Sorry?
What do you mean geometrically when
Well,
you say that a manifold admits?
Yeah, so in order to define a spinor or a manifold, you have to make sure that there's no global obstructions along what's known as this the spinor bundle. And it's a mathematical topic, and I have to admit, I'm somehow not even the right person to ask, but manifolds can be classified in terms of those that admit a spin structure, and it has to do, I don't know if this helps you or not, but with certain Stiefel-Whitney classes being trivial or not. Anyways, it has to do with whether or not there are global obstructions. And what happens is that carrying a spinor around sort of curves in a non-spin manifold leads to obstructions because the fermion picks up a phase in physics terms. If the fermion is charged, you can turn on a background gauge field that effectively counteracts this phase because of the charge itself, such that you cancel it. And so you can have manifolds that, although they don't admit neutral fermions, they can admit charged fermions in the background of certain sort of gauge bundles. And so you see, what's happening here is a little similar. And in fact, there's a theorem that all closed four manifolds at least admit a spin C structure. And so it's almost as good as a spin structure, except that you have to have your fermions also carrying some charge. There's an interesting question that follows that up, which is what if it's a Higgs U1? But that has to do with the presence of Nielsen-Olsen vortices and a billion Higgs model, but it doesn't matter. The point is that, yeah. It could be an interesting requirement if we need all these manifolds that for the standard model to be able to live on these manifolds.
Pardon?
I am a bit confused with the saddle point approximation because in the limit you say it is valid, it is for g times the commercial constant going to 0, but we define the temperature of beta linear with the commercial constant, so I will say that it is valid for a large area. I mean, for small temperature. No? So my question is, looking for the log correction, I will say that okay, if the temperature is lower, they are more dominant, like because it's very similar to black holes. Actually.
No, but this is an expansion that only makes sense in the this you should view as an expansion in small lambda g. If this term starts to compete with this term, it means that, that your expansion has broken down completely. So we are always working in the semi-classical regime where the perturbative expansion is valid. There's a question you could ask whether it's asymptotic or convergent, yeah, if you have sort of all the loop corrections, and that is not known. Yeah, here we're asking the questions in a very sort of systematic semi-classical regime.
Well, but it isn't like very similar, again, like to quantum correction to the black hole.
But even in the black holes, we're imagining always we're in a regime where A over 4G is parametrically large, so that log A is smaller than A over 4G.
Okay.
Yeah.
Okay. I have to masticarlo un poquito.
Masticar. Yeah.
Okay. N equal 4 super Mills is localized in S2.
And S4 also, yeah.
Okay, these results can help in this context, and is a good idea coupling gravity with N equal 4?
Yes, I fully support such approaches, because you see, from this point of view, what we're trying to argue is that all of these localization formulas are coding something very physical. In the localization literature before, it was something we computed because we could. But here, it might actually be an answer to a very physical question. So it adds a lot of physical value to that program. Yeah. Yeah, I like the idea of coupling N equal 4 Spur-Yang-Mills to gravity and seeing whether one can use any tools available. Of course, you would have to, once you start fluctuating the metric, you see, it localizes on a perfectly round S4, but if it's not a topological field theory. So if you put in a wobbly S4, you have to see how much it buys you beyond the, yeah, okay.
I wanted to ask if you could elaborate a little bit on the role of event horizons in this, the computation of the partition function of
the role of event horizons?
Yes.
Well, I think naively, this S4 has no hints whatsoever of an event horizon. Yeah. But it's curious that when you go to the semi-classical regime, you get this A over 4G. That smells like a horizon. You get this term over here, which has this sort of thermal static patch structure, which also seems like there's an apparent thermodynamic behavior because this is sensitive to the residual temperature. But I think the point is that from this point of view, any horizon physics is an emergent thing and an approximation. It's not the fundamental description. Yeah? Yeah.
Okay, thank you.
Okay, I have a follow-up question, so you can keep asking, but I have this one. You draw a static patch, but then quickly we went.
Is it because you're a student mode?
Yeah, I'm in student mode.
Yeah.
But then we went to Euclidean, and we
Yeah.
computed stuff, and we went to S4.
Yeah.
But suppose I start with global de Sitter,
Yes.
and then if I big rotate, I also end on S4.
You end on an S4, but you don't have an argument that you end on the complete S4. In that case, you end on a portion of an S4 in global. But nobody tells you that the range of the Euclidean coordinate should begin and end. So I think from the global point of view, you have a good reason to believe that you end on a portion of S4. But in the static patch, this periodicity of tau closes you onto the full S4. I think that's the distinction between the two.
Okay, I'm not brave enough to say I disagree, but we can discuss it.
You can disagree.
Okay.
But I'm right.
Let's discuss it. Okay. Okay, and on the one follow-up question then. At a certain point you computed something in group theory. You computed and recall this Harishchandra character.
Yeah.
And so in this computation, is it easy to see that we have chosen? I think it does, but I missed it. That we have chosen this static patch metric. Like, are we making summing only over symmetries that are manifest in the static patch?
So at one loop, of course, the fluctuations have to obey the structure and symmetries of the saddle point geometry, which is the sphere. Now, what is not obvious is that you would recover a Lorentzian quantity. So let me re-emphasize this. We did a sphere calculation, and the symmetries of the sphere have nothing to do. It's SO5. It's a very different group from SO4,1 in every aspect, the representations, everything. Nonetheless, we managed to express the one-loop correction in terms of a character of the Lorentzian group, not just some SO5 quantity.
Okay.
So this, I think, is the point to emphasize, that we're really seeing the emergence of Lorentzian physics, at least in the semi-classical regime. And it was not necessarily expected in this context because there was no S1. And so people didn't think that you would see a natural thermal Lorentzian structure, because that was always the idea, is you have S1 times. There was a thermal circle that led to a trace. I have no first principles derivation from Lorentzian physics that I should end up with this formula. In fact, I would very much like to see, and maybe these algebraic approaches and von Neumann approaches will end up refining or computing such a quantity directly from the Lorentzian theory, because there what they show is that if you couple weakly the theory to gravity, then you can make sense of the trace of the operator algebra directly in the Lorentzian theory, and then it would be interesting to see whether you have an agreement with Euclidean and Lorentzian, because this would be very valuable, because we need more evidence for the Lorentzian, for the Euclidean picture.
Okay, thanks. More? Yes.
Can we define an S matrix in the static patch instead of the full?
You can define an approximate estimate. So of course you could consider scattering things like this, yeah? Except for the fact that you, as an observer in the static patch, when you move, your observer moves with you. So this isn't really a location that you can do experiments for, and moreover, it's not an asymptotic region. This is a finite region, and so you cannot use the standard assumptions of the S matrix, like cluster decomposition and this infinite separation of wave packets in this S matrix. It will never be a perfect S matrix.
So the observer must move.
Yeah. What you could imagine doing, which I alluded to previously, is you could, at least as a quasi-auxiliary device, you could imagine removing a portion of the manifold, putting a little tube and defining some boundary conditions on this tube, and trying to define correlation functions along this tube to measure the properties of your universe. And then maybe you have to find a way to average over all possible tubes, to remove it again, or maybe that's the best you can do. But at least here, because you have a little boundary, you could imagine calculating the correlation functions. But the mathematics of GR in the presence of finite-sized time-like boundaries is being developed as we speak. It's not a closed subject. It's a very beautiful problem in mathematical GR. Yeah.
Thank you.
Any more questions?
They are always on this side.
At some point of the lecture, you mentioned that the log of Z was an invariant, but I got lost, and I don't know, like an invariant under which transformation?
There are two senses, or three senses in which I mean invariant. It's a diffeomorphism invariant quantity, order by order in the loop expansion, provided our matter theory doesn't have any diffeomorphism anomalies. It's a gauge invariant quantity, if we also couple the theory to gauge fields. And it's a field redefinition, local field redefinition invariant quantity. So it's a very, very invariant. Yes, that's why I like it.
Okay, so for what's left, we have a bit of whatever's left of the coffee break, and we have a small exercise session or Q&A session, if you want to call it that. But let me ask you to thank our speakers again. And we end on the beautiful note of realizing how much we don't know.